Okay, so today I'm going to be talking a little bit about record types and some of the cool stuff we've been doing in CoolTT to work around a couple of pretty common issues that people seem to experience when building algebraic hierarchies specifically. So been set up quite nicely with the last talk. So a large part of the practice of using a proof assistant effectively is really carefully choosing your definitions so that everything works out nicely. However, there isn't often a single canonically correct choice. There's all sorts of different representations we can use, and some may have better computational content, or some may expose more information in a more convenient fashion. And one way this really manifests is when we're trying to define algebraic hierarchies. So as a case study, let's look at two possible definitions for a monoid. The first will bundle up the carrier type inside of the structure. So here we're saying a monoid is some record. It's got like a carrier type, a binary operation, and a bunch of laws, yada yada. On the other hand, though, we can parameterize over the relevant data. So we can say a monoid is something that takes a carrier type and some operations to a set of laws, essentially. And both of these are important. The second one lets us definitionally constrain the components of structure. So I can talk about, for instance, the specific monoid over natural numbers with a plus and zero as an operation in unit. But the bundled version is more convenient when we want to talk about, say, like all monoids. If we're defining homomorphisms or the category of monoids, that's the one you want to go to. However, to use the parameterized definition, you got to have unification and implicits to be able to even get off the ground. Otherwise, you just get totally owned by just shuffling things around and having 20,000 parameters. It's extremely unpleasant. However, unification is a really hard problem. And as John was alluding to earlier, if you're working on more experimental proof assistants, it's often not the best use of your time to implement unification, especially if you just want to sort of prove out some bigger ideas. You don't want to get all bogged down in the engineering effort required to actually implement unification. And so far, we've managed to avoid writing a unifier in CoolTT. And can we keep going if we want to do sort of stuff with algebra and not get totally buried underneath a boilerplate? And spoiler, the answer is yes. So what does unification really even buy us here? Specifically, it lets us specify that two algebraic structures, or sort of any records really, are defined on the same data. So the canonical example here is rings. You have a monoid and a group, and they need to sort of be defined on the same carrier set. Otherwise, things go totally wrong. However, can we do that in another way? Enter singleton types. The basic idea here is that we're able to quantify over terms that are determined up to definitional equality, and that bit's important. So as some examples, we could have the type of natural numbers that are definitionally equal to 4, the type of types that are definitionally equal to bool, and so on and so forth. Luckily, type checking these with NBE is like really easy. And in fact, in CoolTT, we already have a more general form of these called extension types, which we need for various cubical reasons that I don't necessarily want to get into right now. So with these new types, we kind of get rid of the need for the parameterized representation. If we go back, the whole point is allowing us to specify things up to definitional equality, which is the problem that we were trying to solve earlier. So all we need to do is add some nice syntactic sugar for elaborating a record with some fields constrained. So this is just a little example of some syntax that we might use. So if M is some bundled monoid, so the carrier type's on the inside, we can definitionally constrain the carrier type to be nat, definitionally constrain the operation to be plus, and so on and so forth. And these will elaborate out to a record type with singleton types on each of the relevant fields. Then we can always work with the bundled representation. Throw out the parameterized representation entirely. It doesn't really bias anything anymore because we can just, the only reason we had it floating around is so we could patch things in and constrain things. So, why keep it around? We've just cut down half the library size. And looking back to the Agda standard library, this is a problem that comes up in real proof developments. You have like a 1,000-line file that's all of your algebraic structures, and then another 1,000-line file that defines them as properties, and a bunch of sort of indirection and boilerplate required to interrelate the two. And that's not to knock the standard library or anything. It's the right design decision, but it's just one that's forced on us by our tools. However, this is only half the story, really. We still kind of need unification. For instance, if we think about the type of HOMs for a category, this is a family over two objects into type. If we have operations involving multiple HOMs, so like associativity, composition, we need a huge amount of redundant arguments, like all of the object types involved, essentially, just so we can make sure that the HOM types line up for the requisite operations. And normally that's not a problem. We just hide those all behind implicits and then let unification do its thing. But obviously that requires unification, and we don't want to write a unifier because that's hard. What are we going to do? Well, if we look at that HOM type, that looks a lot like the parameterized representation of the monoid we had before. It's some data defined and parameterized over some sort of set of arguments. And that's the same rough idea as the parameterized monoid. So what if we can kind of use the same trick that we were using before in this context? So specifically, we need to extend the elaborator with the ability to convert a family of the form, record to type, into sort of its quote-unquote bundled representation. So we take all of the things that this family is defined over, you pack them into a record, and then you smack the type family in there applied to all those arguments as another field. So if we go back to the monoid example, this would take the parameterized is monoid definition or whatever, and turn it into the bundled monoid representation. And then we can just reuse the machinery from before for constraining the fields of records to solve this problem. So if we have some family HOM over a source and target object, we can bundle this into a family. So a HOM now has a source as a field, a target as a field, and the data of the HOM as this fiber field. And then we can constrain the fields using singleton types. So if I want to talk about, say, the HOM, the identity HOM from X to X, I can just constrain the source and target fields using the record patching and singleton types. So we can pull this all together into this example. So there's a lot going on here. Let's unpack it. We have this HOM type, which is defined over this. This is the cool TT syntax for records. So excuse me, I wanted to stay true to the source. So we have a record type defined over the source and target object. Then the identity morphism takes an object and implicitly bundles up this HOM family into a record right here, and then constrains the source and target to be X. So all the types sort of are what you would expect them to be. Then for composition, we have some HOM where we haven't constrained any of the source and target, and a second HOM whose source must agree with the target of the first HOM. Then we return a new HOM object where the source field is required to be the same as the F HOM, and the target field is required to be the same as the G HOM. And obviously don't have space on this slide, but one can do similar things for all the laws to make sure everything lines up there. And you get something that's got a lot of the same brevity as what one would get with unification implicits, but with basically none of the implementation cost. So I actually went through and counted all the lines that were required to implement this feature. Obviously, this is a bit skewed because we already had extension types, but it took about 100 lines of code to add all the elaborator features, which I don't know if anyone here has tried to write a unifier for cubical type theory. It takes a little bit more than 100 lines. So that's sort of the broad idea here, and just open the floor to questions, I suppose.
Great, thanks. Questions here from the audience?
Hi. So I feel like your work is kind of similar to a PhD thesis I read few few months ago called the Next 700 Module System, and it talks about a way to like bundle and unbundle modules. Is this similar, or is there what is your take on this work?
So I'm only somewhat familiar with that thesis. It's been in my reading list for far too long. From my understanding, though, that is implemented in the core of the language, whereas this is done all via elaborator hacks. So I think that's an interesting line of research, and it's definitely something I've been thinking a lot about. If we can give some of these operations actual types, and as opposed to just having them live all in the elaborator. But from an implementation perspective, the elaborator version is quite easy to do and doesn't involve really getting your guts and invading the core theory. So that would be the biggest difference to my understanding.
Yeah, that's good to know. Also, there's so just a quick comment that Aaron language also use a very similar way to manage records and type classes. Basically, you implement classes by providing an entire instance, and you can constrain them by fields.
Very cool. Yeah, I think that is the correct way to do things. Moving forward.
Any other questions?
Maybe a quick question. So you said one of the big advantages of this is you don't have to implement unification, but so suppose you already have unification implemented, are there still reasons of doing things this way instead of like using the unification, or?
I would say yes. I still think there is some value there. Specifically, trying to avoid the explosion of bundled and unbundled representations. Specifically in the context of Agda, and I write a lot of Agda. It's quite frustrating if you open the algebra module in the standard library, and implementing any of those records is pretty brutal. And if you're writing your own developments, we've actually run into this a lot in Agda categories, where someone will forget to define the unbundled representation, and then suddenly you'll need it. And you need to go back, refactor a huge portion of the library because you want that unbundled one to be a field of the bundled one. That's a huge breaking change every time you need to do it. So having some machinery that lets you do this patching, I think, is still valuable, even if you do have a unifier.
Yeah, that was also my impression, but yeah, at some point during the talk, it sounded like we're just doing this because we don't want to implement the Unify. But
yeah, it's a nice add-on, but yeah, it definitely does make sense, even like in the context of unification.
Yeah, thanks.
Okay, thank you.